Hello guys, welcome to another video of the course. In this video we start solving the problems of the second chapter, the chapter 2, Transformers. So let's start and see how much time we have today and how many problems we can solve. The problem 2.1, the first problem of the chapter 2, a single phase 4600 volt to 460 volt 60 hertz transformer is connected to a single phase 60 hertz 4600 volt power supply. The maximum flux density in the core is 0.85 Tesla. If the induced voltage per turn in 10 volt, determine A, the primary turns N1 and the secondary turns N2, B, the cross-sectional area of the core. So not too complex. Here is the single phase transformer. We have this high voltage side winding and this low voltage winding. The rated voltage is this one here, and this is the rated voltage of the low side winding. The value of the induced voltage per turn is given in the problem, 10 volt. So here, the induced voltage for one turn of the primary winding or the secondary one, right? These two are the same. ET, the induced voltage per turn, is given. So simply we can calculate the number of turns N1 and N2. This parameter is an important parameter, and later in the next courses, for example, electrical machines design, you will use this parameter to write the sizing equations for design of the single phase and three phase transformers. Anyway, but here we have this number and we can use this equation to calculate the number of turns N1. Okay, the value of the voltage V1 is equal to N1 times the voltage per turn. So the N1 will be equal to V1 divided by ET. This fraction that is equal to 460. So if we repeat the same calculation here, V2 will be equal to this one, and finally we can calculate N2 that is equal to 46. Okay, so this is the part A of the problem. The value of the N1 is this one, and this is the value of the N2. The next part, the cross-sectional area of the core. We know the maximum flux density in the core, and you remember this equation also from the chapter 1. Okay, we used this equation. This is the RMS value of the voltage induced in a coil when we have a sinusoidal excitation. This is E1, the RMS value of the voltage of the high voltage side is equal to 4.44. F, the frequency, that is 60 hertz, times N1, the number of turns that we calculated here in the part A, times phi max. Phi max is the maximum flux in the core, right? So if you consider this cross section for the core, area of the core, and this is B max, the maximum flux density in the core. You know this equation, we discussed it in the previous chapter. Phi max is equal to B max times the area of the core. So if we replace this expression here, instead of phi max, we have this equation and we can calculate the cross-sectional area of the core using this equation. If you replace the numbers, as you can see, the cross-sectional area will be equal to 0.044 meter square. Also, you can check the numbers here. We have solution of some problems at the end of the right reference. So here are numbers for the problem 1. So, okay, let's go for the next problem. Problem 2. The flux in the core of a single-phase transformer varies with time as shown in this figure. The primary coil has 400 turns and the secondary coil has 100 turns. Sketch the waveform of the induced voltage E1 in the primary winding. Yes, we solved a similar problem in the previous chapter. The waveform of the core flux is given here, and we should calculate the waveform of the induced voltage in the primary coil. You know that E1, the induced voltage in the primary coil, is equal to N1 times d phi dt. Yes, this is the core flux. So N1 is equal to 400, and we should calculate derivative of this function. Okay, so here let's also review some equations from the chapter 2, right? This one. This is the equation also explained in the chapter 2, equation 2.1. So, yes, this is the waveform of the flux. And what is the derivative of this function? Is this. In this interval, we have a positive slope. This is a linear function, and its derivative is a constant positive number. Here we have a constant number for flux. We don't have any variation. Its derivative is 0. Its slope is 0. So this is the waveform of the voltage for this interval. And finally, here for this interval, the slope of this line is negative, and we have this waveform for the voltage in this interval. Finally, this and this. So the slope here is 0, here is 0, here the slope is a positive number, here the slope is a negative number, and here is a positive number, and so on. How we can calculate the value of the induced voltage here using this equation? The value of the E1 from 0 to 1 divided by 60, this interval is equal to 400 times delta phi divided by delta t. So this is the number of turns. How much variation in the flux we have? in this interval. This is 0 and this is the phi max. So delta phi is equal to 1.2 times 10 to the power minus 3. The unit is Weber. So this is delta phi, and delta t is equal to 1 divided by 60. So if you replace these numbers, the value of the induced voltage is 28.8. This value, 28.8. And here, similarly for this interval 1 divided by 60 to 2 divided by 60, this interval, we don't have any variation in the flux. Delta phi is 0 and the induced voltage is 0 right here. And in the next interval, this one, interval 2 divided by 60 to 4 divided by 60. How much variation in the flux we have? From this number to this number. So delta phi will be equal to this one. This number, negative 1.2 times 10 to the power negative 3 minus 1.2, this one, times 10 to the power negative 3. So the total flux change is negative of 2.4 times 10 to the power negative 3. And this is the delta t, this interval, the time span of this interval. So the induced voltage here will be equal to negative 28.8. So, and for the next interval, you can repeat the same. Yes. We have a periodic waveform. What is the frequency of this waveform? The time period is equal to 6 divided by 60 or 1 divided by 10. The frequency is 1 divided by the time period is equal to 10 hertz. The frequency of this waveform is 10 hertz. So you can use the simpler and also calculate derivative of this waveform. We did a similar example in the previous chapter, so you can repeat that yourself. Anyway, so let's go for the next problem. Problem 3. A single-phase transformer has 800 turns on the primary winding and 400 turns on the secondary winding. The cross-sectional core area is 50 centimeter square if the primary winding is connected to a single phase 1 kilovolt 60 Hz supply. Calculate A, the maximum value of the flux density in the core B max, B, the induced voltage in the secondary winding. So here again we can use this important equation. The RMS value of the induced voltage in the primary coil is this one. We have the frequency and we have the number of turns. We have the core cross section area, right, is given here 50 centimeter square. The value of the E1 is 1 kilovolt. And finally, we can calculate the B max. So if you replace numbers here in this equation, we will have 1000 divided by 4.44 times 60 hertz times 800 N1, the number of turns in the primary coil, times this area, the core area, that is 50 centimeter square. That is equal to 0.93 Tesla, the value of the B max. Okay, so you can check the numbers here for the problem 3. And what is the part B? The induced voltage in the secondary winding. So we have two equations for ideal transformers explained in the reference. One equation relates the rated value of the voltage, right? The voltage of the primary and secondary sides, and the next one we have a relationship between I1 and I2. So in the ideal transformer we have these assumptions. Okay, the winding resistances are negligible, all fluxes are confined to the core and link both windings, so we don't have any leakage flux. If you see this figure here, in this figure we have leakage flux for the coil 1 and also the leakage flux for the coil 2. By the leakage flux we mean the flux that is generated by a coil but is not linked to the another one, right? So phi m, the core flux, is the mutual flux, right? The flux that is linked to the both coils. And also R1 and R2 are equal to 0 in ideal transformer. The next assumption is ideal iron. We have a core with infinite permeability, so we don't have any core reluctance. The exciting current required to establish the flux in the core is 0. Yes, but we know that this assumption is not true, and in the next section we will discuss the model of the transformer, right? Equivalent circuits. So if we consider these three assumptions, we can write V1 divided by V2 is equal to N1 divided by N2. This is defined as the turns ratio, A, right? A is defined as the turns ratio. Why we can write this equation? Because we have a structure like this. Okay, we have this core and these two coils. The value of the flux phi m, phi mutual, is the same for this coil and this coil. So we can write these two equations. This is the induced voltage for the primary coil and this for the secondary coil, because the phi, the core flux, is the same for both coils. We can divide this equation by this equation and we omit this term d phi dt. Finally we will have this equation. So the next equation is this one, that is derived by calculation of this integral. If we consider this closed path here and write integral of h dot dl, this is equal to n1 I1. The direction of the current is important here. I1, okay, the flux generated by this coil is in this direction. and the flux generated by this coil, this is the direction of I2 is in this direction, right? So this is in the direction of the flux, this is in the opposite direction. So we have negative N2I2. This is equal to 0, right? Because we assume a core with infinite permeability and we don't have any magnetomotive force drop. The value of the H is 0 in ideal case. So yes, when this is 0, we can have this, and finally we have this equation I1 divided by I2 is equal to N2 divided by N1. This is equal to 1 divided by A. Yes, V1 divided by V2 is A, and I1 divided by I2 is 1 divided by A. A is defined here in this reference equal to N1 divided by N2, turns ratio. And we have finally this equation. If we multiply these two sides, yes, we have these two equations. V1 divided by V2 is equal to N1 divided by N2. Yes, the coil with a higher voltage needs a higher number of turns. Yes, and I1 divided by I2 is equal to N2 divided by N1, because the magnetomotive force generated by two coils are the same. The coil with a lower current, yes, must has a higher number of turns. So this fraction, if we multiply this 2, we will have this equation. V1 I1 is equal to V2 I2. And you know that this multiplication is the volt ampere of the primary winding, and this is the volt ampere of the secondary winding. So here you can see the expression. The instantaneous power input to the transformer equals to the instantaneous power output from the transformer. This is expected, yes, because all power losses are neglected in an ideal transformer. Yes. Also, if you write here, we use the lower letters to consider time functions. For example, V as a function of time. And if you use capital letters, the RMS values or amplitudes of these quantities, these phasor quantities, we have this equation. Input volt amperes is equal to the output volt ampere. Right. This is just a review. And if you replace the number of turns, we have N2 and N1 here, 400 turns and 800 turns. We can calculate the induced voltage in the secondary winding, that is equal to 400 divided by 800 times 1000, that is equal to 500 volts. Okay, so just let me explain the transformer models that we have in the Simplorer. Let's add a new Simplorer design for this problem, problem 3. Okay, problem 3. Because we generate multiple Simplorer designs for the problems, I just defined this project, the chapter 2. And this is the model of the single phase transformer that we have from the chapter 1. So here in the basic elements, circuit transformers, we have these models for single phase systems and three phase systems. This is the ideal transformer, two winding transformer, ideal one. Also, we have a two winding transformer with a linear core, a core with a linear magnetic permeability. This is a single phase transformer considering a core with a nonlinear permeability. So this is our case in this question, and I want to solve the part B here using this model, and later we will generate more complex models. So this is a two winding transformer. Consider the dot points also. What is a dot point? You remember from the circuit theory, right? If we have this element, it can be a resistor, inductor, capacitor, a capacitor or a source, right? Anything. The dot point is the point that current enters to the element. So this is the current of the element, and the voltage of the element is voltage of the dot point with respect to this one, V. So in the simpler, when we plot the voltage or current of each element, we should consider this convention. Okay. So here, what is the turns ratio? We have n here, this parameter, but let's check the help of this component. As you can see, the turns ratio is defined as, where is its definition? If you look at this equation here, V2 is equal to N times V1. So N is N2 divided by N1. This parameter here is the turns ratio. In our example here in the problem, the N2 is 400 and N1 is 800. So the value of the turns ratio, this is 0.5 in our case. Save. I'm going to connect the primary side to a voltage source. Yes, this one. And the secondary side, I want to measure the value of the induced voltage. So from here, measurement, electrical, let's select the electrical voltmeter VM1 to measure the induced voltage in the secondary winding. So here we solve the problem in frequency space. Yes, also you remember from the circuit course, the circuit theory course, we can solve a circuit, right, in the static case. When we have DC sources only, we can use the DC analysis setup. Also, in the case of magnetic field or electric fields, we have electrostatic, magnetostatic, right? In the case of circuits, we have DC currents, DC sources. Or when we have arbitrary waveforms, we can use transient solver and solve the state space equations, differential equations using a transient solver, a time stepping method. Or when all sources in the circuit have the same frequency and we have sinusoidal excitations, yes, we can solve the circuit in the frequency space. You remember this from the circuit theory course. So here we add AC solver and we have these properties. The frequency range. What is the frequency range? You know, here is an example. Suppose we have this source. This is Vs. This is a resistor and this is one inductor, R, L. The value of the in the frequency space when we have this source, when we have this amplitude Vs peak value times cosine of omega t. So in the frequency space we have Vs, its angle is 0, right? This source, this is resistor again in the frequency space, and here we have this reactance J omega L. So this is the reactance of the inductor that we have here, and in the frequency space we can solve this circuit considering different values for F. We generated plots, variation of the output voltage versus frequency and so on in the circuit theory course. So in the ANSYS Explorer also we can sweep over the value of the frequency and solve this circuit and monitor the value of quantities. So here you can specify the start frequency that you are going to perform analysis, and this is the stop frequency. Because for single phase or three phase transformers we have 50 hertz and 60 hertz in most of the problems that we have in this chapter. Just I solve this circuit for these two frequencies, 50 to 60 hertz. The frequency is step 10. Just consider these two frequencies and solve the circuit for these two frequencies. So if I analyze, if I run this AC solver in this powerful software, Simplorer, we can visualize the value of the quantities that we have here. So this is the E1, or this is actually the two winding transformer V1. Let me plot it. Here you can see the number. Here the decibel function is used, but I don't need decibel function. Just show the value of the two winding transformer 1.V1. The voltage of the primary side is equal to this one. So 1 millivolt. This is a complex number here. Yes, as you know, we can show the phasor quantities using real and imaginary parts or amplitude and angle. In the Simplorer, also we can display these quantities in both formats. So here I can show magnitude and amplitude. So here I didn't set the value of the input voltage E1 in AC parameters. You should set the magnitude and phase. The magnitude is 1000 times 1.41. Why? Because the amplitude here is this number. This is the RMS value. And you know that the RMS value, Vs RMS, is equal to V peak divided by SQRTO2. That is equal to 1.41. So I considered this multiplication here. And if we analyze the solver again, as you can see, we have this value, and the analysis is done for two frequencies, 50 Hz and 60 Hz. Also, we don't need to show this high number of digits. Field precision 2 is enough. Yes, 2 for the precision. And here, let's plot the V2. Add. I want to show it in the magnitude and amplitude. This, you should select this column, magnitude and amplitude. So here, again, we don't need that precision. So this is the value of the voltage. This is in kilovolt. Consider these units. So you can change the units here. These are peak values, okay? And I can divide this by 1.41. So this is RMS, and this is also, let's divide this by 1.41, apply trace. This is also in the RMS value. So 500 volt, this number. And let's check the angle. This is the angle of V1, 0, but angle of V2 is 108. Yes, we have 108 degrees phase shift between V1 and V2. So what is this and what is the reason? Okay, so you can think about it. We will discuss this later. Anyway, just here I wanted to run this simple example and to be familiar with these elements, how to add the AC solver and run this analysis. So now let's solve the problem 4. A single-phase transformer has 500 turns in the primary winding. When it is connected to a single-phase 120 volt 60 Hz power supply, the no-load current is 1.6 ampere, and the no-load power is 80 watts. Neglect the winding resistance and leakage reactance of the winding. Calculate A, the core loss current, IC, B, the magnetizing current, IM, C, the peak value of the core flux, phi max, and D, the magnetizing impedance, Zm, magnetizing reactance, and the core loss resistance, RC. So to answer this problem, let's review the models of the transformer, the equivalent circuits that we have in the reference. Here in this section, you can check the practical transformer models. So model that we include the effect of the winding resistances, leakage, fluxes, right? To calculate the quantities and also calculate properties of the transformer, such as the efficiency, voltage regulation, and so on. Here is the structure of a single phase transformer. This is the input voltage of the primary coil V1. R1 is the resistance of the primary coil. We include it here in the model to calculate the voltage drop on it. I1 is the current of the primary coil. When we have this current in the primary coil, we have this leakage flux also, the phi leakage 1. This leakage flux is linked to the primary coil only and is due to I1. We have similar elements for the secondary coil, R2, V2, and this is the direction of the current for the secondary coil. So, before adding these elements, this resistance and the equivalent leakage reactance for the coil 1 and coil 2, we can consider this ideal transformer first. Okay, this ideal transformer, and add these two elements. So we have this ideal transformer, and as you know from the previous chapter, we had this problem when we excited one, right, coil. We had these two elements, one inductance to actually model the magnetizing current, and this resistance to model the core losses, eddy current losses and hysteresis loss. So this is the phasor diagram of this circuit. As you can see, in this circuit, when we apply E, this voltage, the value of the IC, right, is equal to E divided by RC. And we know that the IC is in the same phase of the input voltage. And also we have this magnetizing current, IM, that is 90 degree, right, behind E. So the current, this is the total current, summation of IC and IM is this one, I phi. So we can add these two elements to the primary winding, this magnetizing inductance and this core resistance. Then we can add these two elements, inductance for the leakage flux and resistance of the right coil, the primary and secondary. So this is the model of a single phase transformer. However, we have various models, different models. Also, you can check the reference. This is a simple model that we use for low frequency analysis. The frequency is 50 or 60. The frequency is not too high, this model. But when the frequency is high, we have this turn and this turn, for example, and we have a voltage difference between these two turns. So we have a capacitor here, or we have a capacitor between the primary and secondary windings. So these parasitic capacitors, right, are important in high frequency applications, more complex models that we have for transformers used for those applications in power electronic applications. Okay, so in this low frequency case we neglect these elements and just consider this equivalent circuit. So we can simplify this equivalent circuit. As you know, we can shift the elements of the secondary side to the primary side, or shift the elements of the primary side to the secondary side. Yes, we discussed this in the chapter. Yes, you can review the chapter again. So here is the model when we refer the secondary side elements to the primary side. Okay, so in this case also we have the load impedance, referred it to the primary side, and this is the simplified model when we neglect the core resistance and magnetizing inductance. Yes, so because when we have a load current, right, a high value of the load current, the I51, the value of this current, is much lower than this one, I2 prime. So we can neglect this branch, the current of this branch, to have these simplified models. Yes, and these models are used for analysis of power systems. Yes, we have a minimum number of elements because in a large power system we have lots of elements, and simplified models for transformers is necessary. So again, you remember from the chapter, to determine the parameters of a transformer, we have two tests: the short circuit test and the open circuit test, the no load test. In this problem, yes, we use the no load test to calculate these quantities, the equivalent core resistance and the magnetizing inductance. So here is the case. We apply voltage to one coil of the transformer and increase the value of the voltage up to the rated voltage of the coil. Here is connected to the coil 1, this supply. And we measure the value of the current and also the power consumed by the coil. So when we read these numbers, we can determine the value of the core resistance and the magnetizing reactance. Also, we have this short circuit test that we connect the power supply to one coil again, and we short circuit the next coil. We increase the value of the power supply voltage gradually up to getting the rated value of the current in the secondary winding. And then we can read these numbers to determine the R equivalent and X equivalent. So you can review the chapter right, for these two tests. Anyway, in this problem, we do the no load test. So the value of the no load power is given 80 watt. The value of the voltage is given, that is equal to 120. The number of turns also is given here, 500 turns for the primary winding. So here we have this case. We have this model for transformer. In the no load test, we can neglect the resistance and leakage inductance, right? Because the impedance of this branch is much higher than this one that we have for the primary side. So we neglect this part. So we have this circuit. This is the resistance of the core, and this is the magnetizing inductance XM. This is the ideal transformer. So in the open circuit test, the no load test, the secondary side is open. The value of I2 is 0. So this is 0. And this is V of the source. We can call it open circuit or source voltage. This is the source current. And also we have the power, P0 here, or open circuit. So what is the value of the RC? We can calculate it using this equation. RC is equal to V source to the power 2 divided by P0, right? The current of the RC is in the same phase of the voltage. So we can write this equation. And what is the value of the core current? The current of the core resistance is P0 divided by IC is equal to P0, P open circuit, divided by the source voltage, or Vs divided by RC. Yes, or this is equal to V source divided by I source, depending on which one we calculate it first. Yes, if we calculate the current, we can calculate the core resistance using this equation. And if we calculate the core resistance using this equation, we can calculate the core current, the equivalent core resistance current using this equation. So here I calculated the value of the IC, this current that is in the same phase of the input voltage Vs is equal to 80 divided by 120, that is equal to 0.66. And what is the value of the magnetizing current? The current of this magnetizing reactance. This is IM, this is IC, and this is IS. So you know that we have this vector diagram. So the amplitude of IM is SQRTO, amplitude of the IS. This is better if I denote it by the S, and let's denote this by this one, open circuit. So IM is IS to the power 2 minus IC to the power 2, that is equal to 1.45. Yes, this is the magnetizing current. So we calculated the core loss current, the magnetizing current. The next one is the peak value of the core flux, phi max. Yes, we can use this equation again. The value of the phi max is the source voltage times 10 to the power 3, because I wanted to calculate it in milliwebers, divided by 4.44 times F times N1. You can replace numbers. We have N1, we have frequency. So the maximum core flux is zero point 0.9 milliweber. So the next one, the magnetizing impedance, Zm, the amplitude of the Zm. So these are the absolute value of complex numbers, the amplitudes, right? Not the real and imaginary part. So this is the amplitude of the IC. We know that IC is a complex number and Im. So in MATLAB, also I will generate this vector diagram and check the angles. So the value of the Zm magnetizing impedance is Vs divided by Is. Okay, Vs divided by Is is the magnetizing impedance, that is equal to 75 ohm. The core resistance is equal to Vs divided by Ic, that is equal to 180, and the magnetizing reactance is Vs divided by Im. Yes, that is equal to 82.5. So we can calculate the angle of the impedance also. You know that we have this Zm is equal to Rc, right? This is in parallel with J X M, the magnetizing reactance. So we can calculate the angle of the impedance here. So how we can do the calculations in MATLAB? You know, we can use complex numbers and do the calculations in MATLAB. So here is the M file that I wrote for this problem. Okay, this is the supply voltage 120. This is the supply current 1.6, the frequency of the supply, the open circuit loss. So let me rename this to open circuit, no load power loss, and this is the number of turns in the primary coil. Here are calculations. Okay, for the open circuit test, the equations that we discussed them here. So these numbers are amplitudes, and using this complex function, you can define complex numbers. You know that in MATLAB, this variable, if we define it like this, 1 plus 2i, this is a complex number, or z equal to 1 plus 2j. This is also a complex number, I or j. By default, in MATLAB, this is the imaginary number. Okay, so we can define a complex number like this. And what is the class of z? This is a double variable. We have a complex number. The real part and imaginary parts are double. So yes, also you can define a complex number using this function: complex, real part, and imaginary part. Yes, this is another way to define complex numbers in MATLAB. So I defined these complex numbers. This is the complex of Vs, right? This is the RMS value, the amplitude. So I know that the phase is 0 for Vs. So I have set the phase equal to 0. For the core current, the current of the equivalent core resistance, this is IC, its angle is 0. The magnetizing current is 90-degree behind the voltage. Yes, if this is Vs, the voltage phasor, this is Im, magnetizing current. So I set the real part equal to 0 and imaginary part equal to negative Im. Finally, we can sum up these two. This is the complex version of the source current. That is the core resistance current and the magnetizing current, this summation. Also, we have two functions here. I defined these two functions, the add phasor to plot or add the vector to plot, just to generate this vector diagram. So to plot a phasor, we need the one axis. You can define an axis like this in MATLAB. So if I run this, I can generate this axis. Or when you call the GCA, and if there is no axis, MATLAB by default generates one axis. So the first input of this function is the axis. The next one is the phasor that we are going to show, the color, the label, also this is the scale. Because sometimes the amplitude of the voltage phasor is much higher than the amplitude of the current. So we cannot generate this graph correct. So we can specify a scale. In this case, I divided the amplitude of the Vs by 60. And this is the position of the tag. So here, if I run the code, when I consider this equal to 0.5, this tag is in the middle of the phasor. If I write it equal to 1.1 or a higher number, I can write shift the position of the tag. So in this case, the tag is here. When we consider 0.5 is in the middle, just to generate these vector diagrams. And 0.1 is the thickness of this arrowhead. This one. I considered it equal to 0.1. You can increase it. For example, if I consider 0.5, as you can see, we have this big arrowhead. Anyway, so these are just few inputs, and I generated the phasor diagram considering these quantities. So let's run the M file again. You can try the M file, and also you can use these two functions for the next problems also, as we will use. So here is the vector diagram of this example. This is the input voltage. The equivalent resistance core current is in the same phase of the voltage. The magnetizing current is 90-degree behind voltage, and this is the source current. So IS, this one, the name that we used, the source current. Yes. So now let's solve this problem using ANSYS Simplorer and check, can we generate this vector diagram or not? So here, let me copy this and paste it here. This is a single phase transformer again. We don't have the current in the secondary winding. We consider this ideal transformer, and just I am going to add two elements, a resistor to model the core loss. This is RC, and let's add one inductor to model the value of the magnetizing, right, current. So these two are in parallel, and here we have these connections. Yes, that's all. So I am going to set the numbers and recalculate parameters. This is Vs to check if we did the calculations correct in MATLAB or not. So what is the value of the core resistance? 180. Oh, okay. What is the value of Lm? This is inductance. We calculated the Xm, reactance. So you know that Xm is omega L depending on the value of the frequency. We can calculate the value of the inductance. So this divided by 2 times pi times f. The frequency was 60 hertz. This is 0.2188. 0.2188. The unit is Henry. Okay. So what is the amplitude of the voltage here? It was 120. 120. That's all. We can, right? We can run the simulation and calculate the current of the source, right? And visualize the parameters. So let's run the problem 04, analyze to check the numbers that we get in the software. So here, plot the VSI, the current of the voltage source. Why we don't have current here? Okay, we got one error. So let me add a ground here. Okay. So in that case, I think we have a floating point. Okay, so here we get one error. This error is because here we are going to use this AC source. Considering this AC solver, we should select this one, this time controlled option. This is a sinusoidally excited source. Anyway, so now we can analyze the circuit. You should specify this property for the source. Here is the value of the current, Is. Let's show it in magnitude and amplitude. We can divide this by 1.41. Okay, so the value of the current for the 60 hertz supply is 1.6. What is the angle? Is negative 65 degrees. So this is the voltage Vs and this is Is. This angle is negative 65, right? The angle of the Is that we calculated in MATLAB. What is the angle of Is in MATLAB? We can write angle of Is, the complex variable. This is in radian times 180 divided by pi minus 65, right? The same number that we have here. You can add the other variables. For example, the current of the RC. Okay, this one. What is the amplitude and also Im? Let me add. This is the Im. Okay. So in the phasor case, magnitude and amplitude, you can see these numbers. 0.66, the value of the current, the IC, 1.45 for IM. I didn't divide it by 1.41. So 1.45. In the case of 50 hertz supply, the value of the magnetizing current is higher. Okay. So we did the AC analysis for these two frequencies and the angle is negative 90. Right? This is the angle of the IM. So also here you can measure the value of the power. So from here, electrical, you can pick up a watt meter, right? Power meter. And we need to specify the value of the current for this wattmeter and the voltage. So here, this is the voltage and this is the current. So let's analyze this circuit. You can see the numbers again, and if I data table this quantity, the power of this wattmeter is 100. This is a complex number. So what is the number that we have here is equal to 80 watt. So why we have different numbers? Yes, we should check. You can use this equation. You remember from the electric circuit theory again, if we have this element and if we have this phasor for the current and this phasor for the voltage, what is the amount of the power, right, of this element? It is equal to 1 divided by 2 V complex conjugate of I. These are peak values, okay? Or we can write VI complex conjugate the RMS values. So we use the peak values in the ANSYS simpler. So if we use this equation, we should divide this by 2. Yes, you can consider RMS values in your calculations, or you can consider peak values. Because I use the peak values, peak numbers, here I should divide this by 2. Apply. So this is 80. This is the reactive power. This is the active power, 80 watt. Correct? So let's repeat the analysis. If I consider the RMS value here, 120, and run the analysis again. So we don't need to use this number now. This is the value of the current, 1.6. The value of the current for the core, 0.66. The magnetizing current, 1.45. And this is the value of the power. We don't need to divide it by 2. 80. So yes, you should consider peak values or RMS values. And just I wanted to show you the difference, right, between these two type of calculations. And when we use the wattmeter here, what is the P quantity that is calculated inside this element? So let's continue using RMS values for our future simulations and calculations. Okay, so you can repeat the same analysis in ANSYS Simpler, and you can run the MATLAB code to check the graphs that we calculated for this problem. So anyway, I think the time of this video is high. Let's continue solving the next problems in the next video. Thanks for watching.